In the previous video, we started looking at layered structures, 1D periodic stacks, and we started looking at the pathological case where the refractive index contrast between the two layers was actually 0. So we ended up with free space, and in the last video we looked at the band diagram for that particular case. So for free space, and if we assume a sort of like artificial periodicity with period A, we ended up with a Brillouin zone and with a band diagram that looked more or less like this. Okay, so this is what we ended up with in the last video if we have the refractive index contrast equal to 0. So what we're now going to do is we're going to start from this situation and gradually increase the index contrast. So what we expect if we have a tiny index contrast, that we still have something that looks more or less like this, but some things will change. The question is, what will change? Well, in order to answer that question, what we need to do is numerical simulations. And if we do these numerical simulations, we get something that looks, for example, like this for the very small index contrast. In the beginning, there's not much difference, but the main difference starts to occur if we're approaching the edge of the Brillouin zone. So we get bands that look something like this. Okay, so this is what's happening for these lowest order bands. So in essence, what we see happening is that there's some sort of region in frequency space over here where there will be no more solutions. So there will be a gap in the band diagram. And this is then, of course, what's known famously as the band gap. So in this frequency region, there's basically no states that exist in this diagram. Now, what numerical simulations also teach us is that the larger you make that index contrast, the wider this band gap here becomes. And of course, in the limits of 0 index contrast, we end up back in our situation with free space, where there's also 0 band gap. Now, what is the consequence of the fact that we have this band gap over here? Well, let's look at a simple thought experiment. Let's say we have our layered structure over here. So this is an alternating stack of layers with different refractive index. But we're only going to repeat this periodically in one direction, in that direction. And in the lower half here, we just have free space. And then we're going to excite the structure with a plane wave coming from below, from free space, in the frequency region where we have this band gap. And then we ask ourselves the question, what will happen to that plane wave if it hits this periodic structure over here? So pause the video and think about what the fate would be of this plane wave that's hurtling towards our periodic structure. So once this plane wave hits our periodic structure, and if we're in this band gap over here, so remember what this band diagram basically tells us, that's a collection of all possible solutions that can exist to Maxwell's equations, all possible propagating solutions. And we see in this particular frequency region, there's no such propagating solution that exists. So if our plane wave here encounters this periodic structure, it would like to couple to this structure over here, but it cannot really find any mode that will carry its energy forward. The modes there don't exist because we're in a band gap. So if the light cannot keep on propagating forward, then the only possible conclusion is that the light has to sort of like turn back and then actually reflect 100%, because there's no states that it can couple to keep on traveling in the plus z direction. So basically what we've built in this particular case with this band gap structure is a structure that reflects everything, so it's a perfect mirror. The question is now, can we say a little bit more about the origin of this band gap? Where does it come from? And can we explain some aspects that have influence on, for example, the size of the band gap? So that's something we will be doing in the next video. So see you there.